All right, so this is another, so what we're gonna call this section. Maximum problems. This section is very much like related rates in the following sense. There's no new math, no new calculus required. But these are word problems. They'll be central to what you're doing as an engineer or scientist or whatever you're doing. Optimization is all about things like economics, engineering, science. How do we make things optimal? Right? So, again, the calculus in a lot of these things is a lot simpler than, kind of some of the local cultural and derivatives kind of problems that I ask you. But the difficult part is kind of sometimes setting things up. So I'm going to try to do as many of these as humanly possible. Let me start off with this was easier. A farmer has a farm. That borders a long straight line. He has hence and wants to make a rectangle pin bordering river. How does use to maximize it? So he's got a certain amount of fence. He's got a finite number of a finite length of fence, and he wants to border off a rectangular pin along the river. Okay, so just like within related rates, draw a picture to help yourself out. Let's see what this farmer wants to do. He wants to make a rectangular pin on the river. Because he gets to use more fence this way, right? He's raising cows, not manatees, so they can't swim away, right? They're stuck. But let me ask you this. This sounds like something some goofy math guy makes up. Why would the farmer care about maximizing area from a practical point of view? Well, right, he wants big fat cows to sell to McDonald's, right? And he wants as much grass in here for those cows to eat as possible, right? Okay. What else can I do in labeling these pictures like that? Yeah. Okay, and to get in there, I need a length and a width, don't I? Let's call this W and L, right? Okay, we want to maximize area, which, as you point out, is going to come. And the farmer can build a rectangular pin, but he can do it all kinds of ways. He can make the pit, the W very tall, right? Then this way, or he can make it almost down to the river, right? I don't know anybody want to guess what's the shape of the optimal biggest, do we think what the shape is? Well, no, because I'm insisting it's a rectangle, but what kind of? Well, if it weren't for this river, it would actually be a square. So it turns out that if you have a fixed amount of fence and you want to make a square or want to make a rectangle fence, then it should be a square. But because of the fact that we've got this river here, it's changed. What other piece of information do I have? And in terms of my picture here, how can I express that P? I'm sorry. It's the parameter. So in terms of my labels, what is it? Yeah. 2 W's and 1 L. Good. Everybody agree with that? So I've gathered some important information here. My area, this is what I'm maximizing its length times width. And I know that 2 times the width plus the length, that's the perimeter. And this is a constant. P is constant. I can change the W. If I make the W big, I've got to make the L small, or I can make the W small, make the L big. But what is true is this always has it. Now, here's the problem, and this is almost always. L is a variable and W is a variable. And we are still doing, we're not in Calc 3 yet, we're in Calc 1. And so we're doing single variable. Almost always part of the problem is L can change and W can change, but I need to get this down to 1 variable. Any ideas how I can rewrite A as not having 2 variables, but having 1? And then I can shove that back into the equation for A. L is P minus 2W times W, which if you like is P W minus 2W. Might be everybody okay with that? Notice now I've only got 1 variable. A is a function of 1 variable, because remember, P is a constant. Right? It might as well be 2. Right. Everybody okay? So the area is actually given by this crazy formula, perimeter times W minus 2 times W squared. Here is an often overlooked part of doing optimization problems. Lots of people set this up, they write an equation down, and they go bananas. They're fancy with calculus, they're like Gandalf, turning stuff around, taking derivatives. But it is important for you to keep in mind at all times what's your playground. Okay. Here we're going to find the playground. What are my acceptable values for W? Right? I mean, for example, negative W right out. There's no way that we're going to have a negative amount of fence. Right? So it's important for us to say we're trying to maximize this. Don't be putting in negative numbers. Don't make sense of the problem. So think about this problem. What is the smallest that the farmer could make? I'm not saying it's a practical solution. The farmer certainly can do this by being a total Dorcas Mayorkas and taking all of his fence and stretching it along the river. He's not going to feed very many cows that way, right? But he could do it, right? Not a good solution, but there it is. Now, be careful with this. What's the biggest value that the farmer could do? What's it? You're on the right track. So imagine what he does is he sort of exaggerates here. As he varies this, making L smaller and smaller, right? What's the extreme value for L? He can make it 0. And now what's W? P over 2. So here's what he does in the other extreme case. He takes half his fence this way and then the other half down that way. And again, he's got the same problem. Awful skinny cows are needed to fit in that, right? It's not going to work very well. But given the problem, everybody okay? Now, we're in luck. This is a continuous function on a closed interval. So this is just like section, whatever it was, 4.2 or whatever. All we got to do, take a derivative, find the critical numbers, and have the contest. Whoever's the biggest wins. So A prime, derivative of this, my variable is W. This is P minus 4W. So let's find the critical numbers in this range. Well, there's no way this is undefined, but set this to 0. If we set that equal to 0, I get the solution. W is 1/4. Now, all we have to do, this is the only critical number. So all we have to do is check critical number. Okay, let's check the endpoints first. My endpoints are 0 and P over 2. What happens when I plug in 0 to my formula? I get 0. Everybody agree with that? And of course, this makes sense because you think about what you're doing. When W is 0, that's that when we stretch it all along the river, like you get no area out. Right. What happens when you put in P over 2? You get the same thing. Because when you plug in P over 2, this factor is going to get P minus P. Right? And that's when we went halfway up, halfway down, you get no area out of that either. No surprises here. So as long as this is positive, this will give you the maximum. Right? Because at the endpoints, it's both 0. So if this gives you something positive, it's maximum. If it gives me something negative, I've got problems. Let's see what happens here. This is P minus 2 and 1/4 P. All times 1/4 P. So that's going to be 1/2 P. That's going to be P minus 1/2 P. There's 1/2 P from 4 P is 1/8 squared. And I don't know much about that. So this gives minus. Well, that doesn't help the farmer yet because we've got to tell the farmer how to build this fence. So we want W, the 1/4 of your perimeter, and L. So basically, that's 1/4 and 1/4 and 1/2 what you've got. So basically, the length here should be twice what it is. Okay. Any questions on that? Yes.
Still taking this out, but so when we took the first derivatives, and when you said equals 0.
Mhm.
Did we take 4W and put it where 0 is? Is that everything?
Yeah, that's right. So you get another step here. And then divide by 4.
Yeah, so how come it's not, this is my original question. How come it's not like being over 4? Why is it? Or is that the same?
Same. Right. Simple. The calculus is simple, right? Because the only calculus is really from here to here. That's it, right? And the derivative of this is this, right? The difficult part is, and there's an art to it, so you gotta do a lot of practice on this, is actually setting things up, figuring out what your function is, what's your playground. Let's do another one. I have a square. It's L by L. Whatever it is. I cut the squares out each corner and hold up the device. Now, you make cuts. Maximum. Okay, I'm gonna do a preliminary. I'm gonna do better. So I want to make sure that you understand. Okay, there's my square piece of cardboard, right? Can you explain to me what the process here is? How we, so I said something about volume, this is just, of course, a flat piece of cardboard. You might describe the process of what we're doing. See, it says cut equal squares out of each one. Okay. Right, very good. Square out of each corner. So then I cut this away. And now I can fold these up and take them together and I've got a little box. Now let me make a better picture. Now, does everybody got the gist of what we're doing? Got the point out, fold up in the box. Question, and this is very practical. I mean, we're gonna see this, one can see this as being a very practical problem here working at Box Factory is how do I take this piece of material and make a box that holds as much goop as possible, right? And that's what I want, I want the biggest box. How much I won't be able to fit as much into that box as possible. So let's try the picture again with you to kind of figuring this out. Okay. This is L by L. What else should I do to enhance my absolutely dazzling picture? I guess I should mark the cuts. What should I label? Right now, I think still looks a little bit bare. Got the constant L. What else should I be calling something? The one thing that we haven't determined yet is how much to cut, right? I'm cutting 4 corners out of each side, but I don't know what we cut. So let's call this X. Right. What else might be important? Because when I fold this box up, it's going to look like this. What's the volume of the box? Okay, so how tall is this box when I fold those little slats up? What's the height of the box? Right, so the height, when I fold these slats up, will be X. Everybody agree with that? What else do I need to know? Notice the base is also a square. So I'm gonna need to know what the area of that base is. So in other words, I need to know the length of the square. Would everybody agree this inner square is the base of the new box? So I'm gonna need to know how long, so how long is this right here? 2 8 and 7. Get away around. It should be L, take away 2 X's. Everybody agree? So, what are we trying to maximize? We're trying to maximize the volume. And what is the volume of the box? It's the area of the base, right? What is the area of the base? It's L minus 2X quantity squared times the height of the box, which is X. This is what we're trying to maximize. Right. Okay. What should we do now? I've got a function. I know I want to maximize it. There's an important part of the problem that we should probably tackle before we move off into calculus land and start taking derivatives. What's the playground? Okay, so what is the playground? What are the values of X that are accepted? How small can X be? 0. I mean, that's really stupid because you cut nothing out of the box, and now it's just flat. The volume when X equals 0 should be what? Should be 0, right? Because it's still it's just a flat piece of cardboard, right? But there's nothing in the problem that stops us from doing it. It's a stupid solution. It doesn't work very well, nonetheless. Now, how big can I make things? Less than that. X can be as big as 1/2 L. Describe to me what happens when X is 1/2 L. You cut the squares out of the corners so big, you ain't got no cardboard left, right? You cut a quarter of the box out, threw them away, and it's like, oh, I've got nothing, right? The volume of this should be 0 as well, I bet. But, and of course, you can see this from this here, when X is exactly 1/2 L, that's when you've got nothing left for your base. Everybody agree with me? So, again, continuous function on closed interval. So all we gotta do is take the derivative and just compare stuff. Let's take the derivative. This is gonna be a product rule and chain rule. So it's gonna be 1 times L minus 2x squared plus X times the derivative of this, which is 2 times L minus 2x per power of theta. Everybody okay with it? So we confuse up. Well, so this could be minus 4x. Or minus 2x. Right. And when we do one more here, I've got a factor of L minus 2x both things. This is L minus 2x. So it's left over 4x. So I get B prime equals L minus 2x times L minus 6x. So give me, somebody tell me what the critical numbers are. What critical number comes out of this piece right here? Agree. And actually, I like that critical number because it's also an endpoint. So when I check this, I'm doing double reading, right? What comes out of this piece? 1/6 there. So all we have to do now is just size these all up. Okay. B of 0, that means I've got my flat cardboard piece. That should be 0. And if you check the formula when you're putting 0 fractions, B of 1/2 L. This is when you cut the corner so big that you have no box left. That should be 0 too. And if you put in 1/2 L here, you get L minus L squared to 0. And so we're in the same situation as we were last time. As long as this gives me something positive, that's the max. Because it's the only critical number left. Let's see what we get. I put in 1/6 L, and then I get L minus 2 of 1/6, third, and then squared. So this is 1/6 L. We'll see that's gonna be 2/3. So that's 4/9 L squared. So I get, let's just 27. And I don't know much, if that's 0. So let's describe how to do this. Well, describe how to do this. Take your box here. L, so let's see, 1/6 L, so it should be. Each of those cuts should be 1/6 L. That'll make the box as big as possible. Volume. Okay, any questions? The next couple are similar to ones that you're going to see on the quiz. I'm going to do kind of problems here. Describe the isosceles triangle of maximum area. That can be described. Circle of radius. So I made this isosceles, you can actually generalize this. I may actually make a little bit. So here we have a circle of radius R. I'm going to draw this picture to make it simple. Does everybody remember what a isosceles triangle means? What does that mean? Two of the sides. Two of the sides. So that makes it a little bit easier. So I'll take the vertexes between the two equal sides and put it at the top. So triangles will look like this. Now I can vary my isosceles triangle. It can be way up here toward the top, got kind of a fat bottom, or it could be all the way kind of skinny down here. And the question is, what's the maximum area that I can make here? Anybody want to guess before we start? What's the maximum area, or what does the triangle look like? And that's the maximum. So I don't think the maximum area is up here. It looks like the red one's bigger than that. Everybody agree? It also looks to be like the red one's bigger than the skinny one right here. But somewhere in the middle, it ought to be as big. You want to guess what that looks like? So sure. Oh, you mean like right here? That's a pretty good guess. But actually, as you move down a little bit, it does get. So let's see. Let me draw the picture. Set up here. I'm gonna use words here. So this is the circle x squared, y squared. And I'm gonna call this point right here x one. And somebody described to me. Oh, by the way. This point right here at the top is x equals 0, y equals 1. Do I agree? And somebody give me a formula for the area of that triangle. Okay, it's 1/2 base times height. I'm going to call this the base. It's like 1/2 of that base is in terms of what I've got labeled on. This distance from here to here is just the x coordinate, right? So 1/2 base is the x. Right. What's the height? Here's the question. Everybody read the height of the triangle. Wait, somebody tell me how tall that is. So quick. How did you do that so quick? Just took the top, my bottom, right? That's how you measure height. No different here. What's the y coordinate at the top? R. What's the y coordinate at the bottom? There you go. So it should be, you're doing exactly this thing. Top minus bottom, R minus. And this is the height. Good. So, okay, here's my usual sucky problem that I always get in these kind of things, and that is I got too many variables. I can change x, I can change y. How am I going to get this down to one variable? I need some way that two variables is fine. There's something on the board that I can use. Exactly. So this is an equation that relates x and y. Right? So I can get rid of one variable. Now, if you want a to be a function of x, a function of y, you can work from both ways. What is decidedly easy? I would rather have a be a function of y. It's like only y. Because you have to get the problems with this, right? See the way I've got this picture drawn? If I tell you x, y, right, this x, y point determines what the triangle looks like, right? Because once I've got this point, it's mirroring the point, it's always at the top. Now, let me point something out. The y coordinate, the x coordinate is not. Because all the information I give you is the x coordinate. It could be this triangle or this. Two different triangles. They both have the same x coordinate. Right? But if I tell you the y coordinate, that's it, baby. You know what it is, right? These have two different y coordinates. Now, like I said, you can work it either way you want, but I highly recommend we do this shove that in for X. Because that'll give me a function of Y, and it's easier to deal with, because otherwise I'm gonna have to deal with it. in a couple of cases. That's the way I want to do it. Okay, everybody with me. Square root, it's the 1/2 power. Is that okay? Okay, let's not forget, what do I like to do at this point? I've got my function. I need to know my playground. Yeah, before I do the derivative, I really want to know my playground. What's the smallest value for Y that I can get? Here's a little bit. What's the smallest value of Y? It's purple. Very good. If Y is -r, I've got Jim's stupid stick triangle, right? Not like a triangle, is it? But there's nothing in the problem that prevents it. Okay, what's the other extreme? How big can it be? It's right. Jim's little pointy triangle, right? It doesn't give you much of a area, but. Oh, I'm digging this. Continuous function, closed interval, yet again. Right. 2 examples. At this point, let's take derivative. Derivative of this. What's the sign? So I've got the derivative of this 1/2 log minus 1/2 plus 2y. That's the other piece. Plus r squared minus y squared 1/2 comes the derivative of this. But I tell you what I'm going to do. I'm going to pull out just a little bit. This here is minus y. R minus y. R squared minus y squared minus 1/2. Let's set that up a little bit. Minus r squared minus y squared. Oh, I'm back. Okay. I'm going to pull out an r squared minus y squared minus 1/2. So that's gone. That leaves me with minus y. I'm sorry, minus y. And that's going to leave me with minus r squared minus y squared to the 1/2. Checking if I multiply back, this just puts this back here. And when I multiply these two, this is r squared minus y squared minus 1/2, r squared minus y squared 1. Now notice that this piece right here, so say right back. This piece is r plus y equals r minus y. Like that. Minus y, minus r plus y, or minus. Now, you might think I'm just showing off the algebras, that, but it's easy to get there. It's better for us to get this over with, so we'll be able to figure out everything. And what's left here, this is r minus y. And here. This first piece of parentheses is minus y minus r minus y. So that's minus 2y minus r. And the other piece to r minus. So I get some critical numbers here. Right, so one more time, I'm gonna pull minus like a first factor. So at the end of the day, I got a prime minus pull the minus out of that factor, 2y plus r minus. And now, since I took the time to do it, it's kind of easier now, I think, to pull off the critical numbers. Okay, so I'm gonna do a little elimination here. The first thing I'm gonna do is, let's see, y equals minus r and r, make that undefined. This gives me y equals minus 1/2 r. And this gives me y equals r again. So this one's a repeater. And it's an endpoint. Right? In fact, r shows up as a critical number twice, and it's an endpoint once. So that's three things down to one as far as checking goes. Any questions on that so far? Did you all follow the algorithm? So now we've got a test like this, right? Most of it, so here's what we need. We need a minus r. We need a of r minus r, and a of 1/2 r. All that. Now, a of r and a of minus r, on my point triangle and my tall skinny triangle, they should be 0. But you can check here, when I plug in r or negative r, I get 0 in this term right here. So these are both 0. And the 1/2 r gives me something else. Let's see what this is. If it's positive, then when I plug in 1/2 R, I'm sorry, minus 1/2 R. Including minus 1/2 R, I get R squared minus 1/4 R squared. Square root of that. And then I get R minus 1/2 R. So this is 3/4 R squared 1/2 times 3/2 R. And that's going to be 3 radical 3. Radical 3 over 4 R. This is bigger than 0. So y equals minus 1/2 R is max. So let me draw you a picture of this. So your guess was down here for the diameter, which is a good guess, but actually since you need to go forward, you need to actually go halfway down. So about right here. About right here. Here. That's the maximum final inside there. Do you know what's true about this triangle? It's a special kind. All the sides are the same. In fact, if you you can measure the size if you want to put these points, measure this, or you can think about rotating this 120 degrees. 120 degrees is to go up here, and this goes exactly there. So if you want to put a triangle in there, it takes the most possible area out of a circle. You have to do it with all 3 sides the same. Any questions? Okay, I'm going to do something similar, different, but actually very similar problem. Find the largest volume inside a sphere. Right. This is almost the same problem as the previous one, except it's now in an exponential dimension. So you might guess what the answer is. Let me write a picture of this. I'm going to draw a primitive picture first, and then make a better one. So here I have a sphere, radius r. And I want to find the cone in here that has volume that is big as possible. So inside this sphere, ball, I put a cone, ice cream. What was described the cone that has a big point? Again, you can have a tall skinny cone, or you can have a short fat cone, which has the biggest part. Everybody understand the problem? Okay, so let me draw a picture of this. Try to set this up. So I'm gonna draw the 3D model, and then I'm gonna back out some symbol. So however the cone looks, I can arrange it so the tip of the cone is going forward. This is confusing. It's all three. So let me see if I can get it. Simply. It gets down to brass tacks. How about this? Let's look at a cross section. That is, bring down a guillotine, cut that half what's inside. And a cross section will look like this. In fact, it looks very similar to the previous problem. The funny thing is, as we go along, we'll see that despite the fact that we're now dealing with a higher dimensional object, what we're going to end up doing is easy. So when I cut right through the middle of it like that, my sphere now looks like a circle, right? What does my cone look like when I cut it like that? It looks like a triangle. So I've got almost the same situation as I had last time. I'm going to call this x, y, and my circle is now x squared plus y squared, r squared, just like we had before, because after all, the circle and radius are. But difference here. By the way, the triangle that took up the most room with respect to area was the one that had all equal sides, right? That's what we showed with the last problem. What do you think the triangle for the largest cone is going to look like? Cross section of the largest cone. You would think, right? Because this triangle takes up the largest area, right? And so when you spin it around, it should take up the largest volume. I find that a little surprising, don't you? Maybe we can figure that out. Let's see what happens. So, what we want to do is we want to maximize volume. Now, let me see. Got it. I'm going to draw a little cone over here. By the way, this is something that I'll give to you. You get into top 2, for example, would be derive this. Does anybody know what the volume? I've got radius r, bottom circle of radius r, and it's got height h. The volume of the cone. Anybody know what it is? That's right. It's 1/3 of base times the height. And in this case, the base is a circle and the height is h. So let's imagine spinning this around. This is the cone. The volume is 1/3. The base is pi x squared. And the height right? Because if you look here, the radius of this cone is x, x. So it's 1/3 pi x squared, there's your circle part, times the height, which is r minus y, just like here. Everybody okay? Questions? Now, we've got our usual problem that almost always seems to show up here, and that is, shoot, got too many variables. X can vary, Y can vary. I need something to place. And here, once again, I use the same equation to relate this. We had to think about it here, but it's easier to see that I want to substitute for X, right? Because to substitute for Y, I'm going to need to take a square root. But notice that X squared is R squared minus Y squared. And so I can improve my volume formula, and it doesn't even need a square root. My volume is 1/3 times X squared, which is R squared minus Y squared times R minus. So what do we need now? We need our playground. And in this case, my playground is the same as your Y coordinate can go all the way down to the South Pole, being -R, and all the way up to the North Pole, being now, let's take a derivative of this. Derivative of this is minus 2y times R minus Y. R squared plus Y squared, the derivative of this, which is negative. So I'm going to pull 1/3 pi of this. And we get minus 2y or minus y plus minus 1 plus 1 or minus. And all I really did here is I pulled up 1/3 pi, and then I back. And notice I've got a common factor, which is the point of doing this. This is minus 2y minus R plus y. So R minus y, which in the final bit is going to be minus 3y minus R. R minus y. And so derivative 1/3 times 3y minus R, 3y plus R, y minus 4. All I do is I took the minus sign out of that and turn around y minus R. This makes it fairly easy to pick out critical. Can somebody tell me what they find critical? Not X. Critical number Y R and and endpoints. So let's check them all. I'll plug in either bar or negative bar. And finally, all I have to do now is plug in -1/3 R. And if this gives me something positive, then that's it. It's the minus. R squared minus 1/9 R squared. And we'll see R minus 4/3 R. It's R minus a third. Plus 8/9 4/3. So that's 32. So that's going to be 32 over 81. And this is equal to 0. So all y minus 1/3 R. And somebody, this puzzles me a little bit because what this says here. So you go halfway down to the maximum area. The maximum area should be this triangle, which is supposed to be equal sided. This says you get the maximum volume, you don't go down quite. The red triangle takes up less area. When you spin it, it takes up more volume. Anybody explain why? Because actually, the volume total, it's a square by the radius, but only linear by the height. And so making it a little bit fatter adds to volume. Right? So, but that's, I think, a little bit about it. Okay, any questions? Okay, here's another one. Or making soup. Whole. So you might wonder why cans are shaped like they are, right? I mean, if you go buy a can of soup, and you notice that in grocery stores are always kind of the same sort of general shape, right? No, if you ever see a soup can that's like only an inch tall and as wide as this, right? Never seen one. I mean, of course, there is a practical problem having to put them on the shelves there, right? But there's actually a reason. So suppose that you're trying to make a soup can to hold your Prego soup, and you've got to put 16 ounces in there or something. We'll say it's specific volume thing. It costs 2 cents per square inch to make material side and 4 cents per square inch to make tops. And by tops, I mean the top and the bottom, right? So I've got a cylinder can. This. Cost for making this, the wraparound stuff is 2 cents per square inch. And tops and bottom, 4 cents square inch. Now, the question is, find ratio of H to R that maximizes, I'm sorry, minimizes. So here's the radius of your can, here's the height. I want to know what is the ratio of H to R, right? Is H twice as big as the radius, 3 times as big? Is it half as big as the radius? What minimizes the cost of making this? Right? Because after all, that's what you're doing. You're in the soup business now, and you want to make as much money as you can. And one of the ways that you do that is make your costs, including making cans to hold this stuff, as cheap as possible. Okay, what are we minimizing? We're trying to minimize the cost of this can. What information do we need? Well, let's call this, well, I don't know, we'll call the radius X. We'll call height Y. Let's take this apart bit by bit. Cost of top and bottom. How much is that going to cost you, Mike? And I'll do this all in cents. We're writing 0.04. Well, so here's what you know. You know it costs 4 cents per square inch, right? So if you want to know how much this costs, you got to know how many square inches you do, right? How many square inches am I dealing with? What's the size of that top in square inches? The area of that top is pi squared. I agree. And if X is measured in inches, that gives me how big the top is. But I don't just have a top, I have a top and bottom. All right. It's a circle. Okay. So the top is pi x squared, right? That's the area of it. The bottom is pi x squared too, so there's 2 of them. And now I got to multiply that by the cost, which is 4. So that's how many cents it's going to cost me. 4 cents per square inch, and there's your square inches. Everybody agree with that? What's the area of the wraparound side? Well, let me answer this. Imagine I take a pair of metal shears and I cut this. I suppose I just got the side of the pen. And then I unroll it and pound it flat. What does this look like? Right now. So the height of this rectangle is Y, right? Because that's what the height of the can is. What's the width of this rectangle? So it's the unrolled length of this unrolled. It should be the same as the circumference of the circle. You agree with that? The unrolled length should be the distance around that circle, which in this case is right here. So the area of the side is 2 pi x y, right? And it's what? What is it? 2 cents per square? So I'm gonna write T for the total cost is going to be 8 pi x squared plus 4 pi x y. In cents, that's how much it's going to cost me to make that can. Now, what problem do I see? Seems to always rear its head. Got too many variables. Dagnabbit, I need to get rid of one of those variables. There's another piece of information in this problem. Anybody figure it out? Well, it's sort of subsumed in the cost we did, but look back at the original problem. What is the volume of this? Volume of this is supposed to be fixed, right? 12 ounces or 16 ounces, however, with soup I want to slop in there. The volume of this is pi x squared. Right here. Area of the base times the height. So now, remember, B is constant. This is just a number. So, of course, when you make x big, you have to make y small. You make x small, you make y bigger. So, now, look at this equation. I'm either going to solve this for x and shove it in there, or I'm going to solve it for y and shove it in there. Which one's better? I agree. You can do it either way, it will work out, but if I solve this for x, there's a square root involved. And nobody wants to be messing with this. If I solve it for y, it's a lot cleaner. And so, finding this and this, I get my new and improved cost function. 8 pi x squared plus 4 pi x times y so T 8 pi x squared plus 4b over x. So now I've got my function. What should I be thinking about now? Good, good. I need my playground. What's the smallest value that I can take for x? Oh, and all the previous ones, we've had a distinct smallest value. There is no smallest value. So I explain why. I mean, certainly x cannot be negative. There's no doubt about that. But it also can't be zero. Why can it not be zero? Look at this equation here. Maybe I wanted 16 ounces of soup to go in my pan. What happens if this equation if x equals 0? Leave with 0, and there's no way I can 16. And in fact, this is kind of a dead giveaway too. X is a no-no. X is a no-no. How small can I make x? There is no smallest, but I can make it any positive number. I mean, I can make that x so small that the soup can is taller than the Eiffel Tower, right? That's probably not a very good solution, but I can certainly do it. I just can't make it 0 because once I make it 0, I can't fit anything into the can. And again, like I said, problem here sort of gives you a hint, 0 is a no. Now, how big can I make X? Well, there's no limits at either. I mean, I can make X like, I could make X 1 mile wide if it, not very tall at all. And it holds 16 ounces, right? That's not a very good solution, but anything goes. Now, this is a little distressing. What makes this a little bit different about the problem? My playground has no inputs. And remember, we did all that optimization with get continuous function closed input. Here's the problem now. This is very important. When you don't have inputs, you need to somehow verify that you get a maximum minimum, right? So let's go through this. I know what my playground is. From here on out, it's very similar to what we did. Let's take the derivative of this. This is 16 pi x minus 4 b over x squared. Everybody okay? That's the derivative of this thing. Now, of course, one critical number is x equals 0, but lucky for us, it's not in the range, right? In fact, it's not a critical point. It's not so let's just set this equal to 0. And so I get 16 pi x cubed minus 4b 0. So I get x cubed is 4b over 16 pi, which is b over. So I get x is the cube root b this is 4b x minus 1. Right, so its derivative is minus 4b x minus 1. Now, what was the goal of this problem? What were we trying to do? We've got one critical number here. Here's 0. Here's, I don't know exactly where it is, but I don't know much, but I know that the cube root of b over 4 pi is certainly a positive number. Right? B 4 pi all positive, cube root that's positive. So I've got some critical number out there. Now this is a very, very step to go. Problem. What have we got here? We've got a critical number. A lot of people say, oh great, this is the man, we're done. But how do you know that critical number is not a maximum? Right? What if you do this problem for your boss? Your boss says, hey, we got to make these soup cans as cheap as is humanly possible. What do? You solve the problem, say, oh, I get a critical number. There's your man, boss. What if what if that's a maximum? And now your boss is making the most expensive soup cans possible. You are so fired, right? So we need to make sure that this is doing for us what we want it to do for us. So B prime C. No. This should be T prime. Okay, I don't have any numbers here, but it's no worries. What happens when there's only one critical number here, and it's this one? What happens when x is stinking close to 0? Everybody agree this is almost 0? And this is huge negative. So you're stinking close to zero, you're negative, so you're negative everywhere on that side. Critical number. Now what happens when the X is huge, very large positive? This is humongous, and this is very, very tiny. So what happens here? Down, up. This is a local min, and in fact, it's an absolute min. On the interval that we care about. And how do I know that? Because these are all the ranges that are acceptable for X. So it goes down and then it goes up forever. That is an absolute min. So this is the optimal. Let's answer that. Actually, the last thing that I asked him, his problem was, what is the ratio of H to R? Which in our case is Y over X. Well, let me see here. The Y is B over pi X squared. And X was cube root of B over 4 pi. And let's see. Yeah, that's my Y here. And this is my X. And so I guess what I can do to make this better is well, let's see. Oh, yeah, I know what X is. X is also, let me do this. Y is B over pi X squared, and X is just X. What am I talking about? 1 over X cubed. And X cubed X cubed is B over 4 pi. To basically be 4 times the radius or twice the diameter. So that the can should be basically twice as high as it is. Questions? Okay, be careful when you're on an open interval like that, or one where you don't have the input, because at some point you need to verify that what you have is actually what you claim, that is, it's a maximum or minimum. I'm going to give you one more before we take the quiz. Example, a person wants to get to the other side of the lake, say circular lake. No crazy. Person can walk twice as fast as they can grow. Describe now get the opposite side. Okay, so here's the situation. This lake has radius R. And a person wants to get from here to here in the middle of time. And they can walk twice as fast as they can row. So they've got lots of options, right? They can walk, they can row straight across. And of course, rowing straight across is the minimum distance, right? Or they could boat for a while and then get out and walk for a while, right? So maybe I'll go over here, get out and walk the rest of the way. We want to minimize time takes. Okay, let's suppose person rows at velocity v. Notice it didn't tell me in the problem what that velocity is, but and I know that the person walks at velocity 2v. They walk twice as fast as they row. Let's suppose they take off at angle theta. And then walks the rest of the way across. So we're going to assume that the person runs that way, gets out. I want to see. Rowing time. Well, I need to figure out some more distances here. Let's look back at this. I need to know how far they row and how far they walk. Right? Everybody agree that they walk this far? And they row this. Notice that rowing time is distance over velocity, right? That's how far they go, feet, how fast they row feet. Do I agree with that? V is constant, V varies. Okay. And the walking time is S over 2V, where this one here is S. Oh, now, here's the problem. D varies, S varies, and really don't have much good for them. But I ain't going to get D and S in terms of theta. This is an exercise kind of in geometry. What's the length of this from here to here? It's the radius of the circle, right? What's the length from here to here? Radius of the circle. So this is also R right here. What's this angle? Anybody tell me? Exactly. It's exactly the same as the other one. So, anybody now tell me what this angle is? This one should be twice. Does anybody see why? Look at this triangle up on top. Theta plus this is 180 degrees, right? Also, this plus this is 180 degrees. So this angle should come to what these two. That's theta plus theta. Everybody agree with that? Okay, somebody tell me what S is. It should be this angle, theta, radius, so. Y'all remember this thing, area of the second circle, you have like radius r theta, and this S is equal to theta. Listen important. Well, here's the way I always remember. What happens when theta is 2 pi? When theta is 2 pi, you've gone all the way around the circle, and the formula gives you 2 pi r. What happens when theta is pi? You've gone halfway around the circle, and theta is pi, and so S is all pi halfway around. Well, I've seen this. What about D? If I call this bit right here Z, and D is 2Z. And this is right angle. So Z, and this is R. So Z is R cosine theta. Okay, any questions on that? Time taken. Well, it's the rolling time plus walking. So it should be 2R. There's rolling time. 2B. And walking time you divide by 2B. So I divided my S by 2B and I divided my D by D. There is, this is how much time to get around the lake in terms of theta. What's my playground? What's the smallest value theta? How small? Zero. And what does this mean actually physically? I think that is 0. Go straight across in the boat, no wall. This is all boat. What's the biggest thing? Well, actually 90 degrees, right? And that just means that you just take off walking. But I mean, when you get to 89 degrees, it's almost stupid because you have to get the boat. And if you go 2 inches, you know, walk, right? So let's do this. T prime is 2/v. Well, minus 2 sine theta. Plus 1/v. Remember, theta is my variable, so that's gonna be minus 2v. And seem to, yeah, I seem to be totally freaked out. I've got my R's. They should all be there. There. B is a constant, right? It's just a constant rate that you know. So actually, theta is the only variable here. This is never undefined. So let's set this equal to 0. And in the range from 0 to the power of 2, I get minus 2/v r sine theta minus 1/v r is equal to 0. So I can cancel a bunch of stuff, these and the r's. So actually, here's one of the things that kind of is a good hint in this problem. The r's cancel and the v's cancel, which means neither r nor v makes a difference on the answer. And actually, given the fact that it's a circle, this answer should only depend on theta. It shouldn't matter how big the circle is, and it shouldn't matter how fast you row the boat. It only matters that the ratio between the walking speed and boating speed is constant. So if I get rid of the v and the r, I get minus 2 sine theta minus 1 0. So solving this, I get sine theta is equal to oh, that should be a plus. There we go. Sine theta. And the only place that sine theta is 1/2 between 0 and power of 2 is at power 6. So now all we have to do is test. T of 0. This is all both. How long does it take you? 2/v r, that equals 0, so that's 0. So I get 2/v times r. T of power of 2. This is all walk. Now the cosine of power of 2 is 0, and I get r/v times power of 2. T of power of 6. Well, this is r/v times 2. 2 times cosine of power of 6, radical 3, plus r/v power of 6. So I'm going to clean this one up a little bit. It's r/v and radical 3 is power of 6. Anybody tell me what the person should do to minimize time? This is r/v times 2. This is r/v times power of 2. Which one's smaller? Agreed. This one's winning so far because it's shorter time. Power of 2 versus this thing. Can you tell? This is more than 1.5. And this is more than 1/2. So this thing is actually more than 2. This is actually the max. So the critical number here, if you rode at power 6 and then got out and walked, that takes the most time. So you don't want that. So this is an example of the critical number actually gave me something I don't want. It gives me the maximum. The minimum is all walk. So ensure that you investigate these things are giving you what you want. Okay, there's a lot of these problems and the homeworks and all my little things and stuff. You need to, the calculus isn't very difficult, but you need to practice on this quite a bit. Any questions?